Good morning and welcome to this next lecture on sound and structural vibration. So far in so many lectures we have seen the classical problem, as I call it. We pose the problem, we went into the Fourier domain, okay. We decided to do the work in complex domain. So we learned some rules in the complex domain. We used branch cuts. We learnt about asymptotics. Okay. We looked at the velocity, plate velocity, and the related acoustics. Uncoupled and coupled. And we understood the important frequency regimes for different physical effects. Okay. I am writing this because this kind of gives you the gamut that is involved typically in sound and structural vibration problems. Okay. Now the problem we looked at was infinite dimensional. The panel was infinite dimensional. The sound field half space was infinite dimensional. Okay. I mean extends to infinity. So we are going to look at the next problem now. The next problem is this. I will call it a 2D structural acoustic waveguide. Okay. What is it? The geometry is this. I have a 2D channel of acoustic fluid. Okay, there is acoustic fluid here. And this channel extends to infinity in both the directions. And has a height A. Okay. Now the top is rigid. This surface is rigid. Okay. And bottom surface now can carry a flexural wave. It's flexible. Okay. Bottom is flexible. So from the earlier problem here, one dimension is bounded. In this direction it is bounded. Okay. In the other direction it is infinite, but in this vertical direction is bounded. and let me say my coordinate system happens to be x in this direction, y in direction here, this is my y0, the bottom is my y0, top is y equal to a. Okay. So what is going to be revealed, or what is interesting about this problem? The fact is that if this flexural plate, the bottom plate, okay, flexural, was placed in vacuum, okay, then it will carry a flexural wave, okay, unaffected by any fluid. On the other hand, if there was a rigid duct, rigid 2D duct, rectangular 2D rigid duct, then you will have various waves propagating. You will have a plane wave propagating, then you will have the next cut on propagating, which has 0 velocity at the walls, 0 velocity at the walls, and then you will have the next level wave cut on propagating, okay, and so forth, and all higher orders which all start with 0 velocity here will be propagating, okay. These are higher order modes of a duct. So this comes from acoustics, which I am not going to repeat, okay. One should know this from acoustics. So uncoupled from the other medium, the flexural plate placed in vacuum, or this acoustic fluid with rigid walls, okay, with rigid walls, the walls being rigid, they behave uncoupled in isolation, okay. But now we are going to place an acoustic fluid in contact with a flexible plate. So the fluid will see not a rigid boundary now, but it will see a flexible boundary. Similarly, this flexing plate will see an acoustic fluid applying pressures to it, okay. So this is a coupled problem. That means as the flexural wave propagates, the pressures in the fluid will be applied back, they will influence and change the behavior of the plate, and the acoustic fluid carrying its own cut on waves, plane wave and higher order modes, will see the flexing of the nearby boundary, and so their behavior is going to be modified. So each medium will modify the behavior of the other. So this is a coupled problem. So this is going to be interesting to look at, okay. So let us see. So again, this is my geometry here, 2D waveguide. So top is a rigid plate, bottom is a flexible plate. My y begins here, y is 0, y equal to a, okay, and they go off to infinity in both directions. So we will formulate the equations for this system, okay. Now so let us see now the acoustic fluid. It's a 2D domain, right? It's a 2D domain. And so the related acoustic wave equation in pressure is del 2 p x comma y comma t del x square plus del 2 p by del y square x comma y comma t is equal to 1 over c squared del 2 p by del t squared. This you should know from your acoustics background. Okay. So what is the general solution to this? We are looking at harmonic sound fields. Okay, that was the statement I made right in the beginning. So if this system is somehow driven at a harmonic single frequency, the general solution is this: a e to the power of I omega t minus kxx minus kyy plus b e to the power of I omega t minus kxx plus kyy. Okay. So I am looking at waves that are propagating back and forth, up and down, and propagating in one direction. Okay, that's adequate. So this is not the most general in that sense, but that is adequate. So far off on the left there is some source which is localized source which disturbs this system, and so now the waves are propagating in the positive x direction and they are propagating up and down in the y direction. So that's this solution. Okay. So this minus sign here and here says that the waves are moving towards the right. Okay, and this minus sign says they are moving towards the positive y direction, and this plus says the waves are moving in the negative y direction. Okay, and one more statement I should make is that the classical problem that we did, I use the e to the power of minus I omega t convention. Okay. So approximately half the world uses this negative I omega t convention and the other half uses the plus I omega t convention. Okay. So unfortunately it's confusing for the students, but what to do? And the reason I used the negative I omega t for the classical problem is the entire literature, which is very rich and studies this problem, uses this minus I omega t. Okay. So if I now suddenly change the notation, the student will go, when he reads the paper, is plus I omega t, and that difference makes a lot of difference in the branch cuts. So it'll cause more confusion than use. Okay. So I kept it that way. So if you have looked at that problem the way I presented, and then you go at the look at the literature, you will not be confused about the notation. Whereas I myself am comfortable with plus I omega t. For the rest of the problems I will use plus I omega t. Okay. In the long run, if you understand what's happening, there is no problem. Okay. You can do it both ways after you understand, but at the learning stage these are very cumbersome if the notation is changed. So this problem I am going to do with plus I omega t convention. Okay. So now, having said that, so we have this solution for the pressure field, okay, and where let us see kx is the wave number in the x direction and ky is the wave number in the y direction. Okay, so that now you should know kx square plus ky square should be equal to the acoustic wave number square, which is omega square by c square. Okay, c is the speed of sound. Okay, so that's for now the information about the acoustic fluid. Okay, and A and B are so far unknowns. O and B are unknowns. Okay, there are more unknowns here, but A and B are unknowns. Frequency omega is known. Okay, so kx and ky are still undecided. Okay, now what about the panel? So, or what about the plate, that is the boundary? The plate, it's a 1D plate as before. Okay, so it's a 1D plate, that is the boundary. So what is the equation governing that? It is E h cube by 12 1 minus nu square d4 w by dx4 minus rho ph omega square w of x is equal to minus p x comma 0. Okay, so the time behavior has been removed because it's a linear system and every variable vibrates at omega, that has been removed. And so now, because the y dependence, what I mean is the z dependence for the plate in the other direction, okay, the z dependence in the other direction is not there, so it's just dependent on x. So I have written it accordingly. The time has been removed because it's harmonic. The z dependence has been removed because it's the way we have posed it, and so the displacement w, the displacement w of the bottom boundary is a sole function of x. So this is the equation, and now there is a pressure that is applied on it from the fluid. Okay, so there is a pressure acting on the plate, bottom plate, due to the acoustic fluid. That's this term here. That's this term here. Okay. Next. Now we know that we have two equations, the fluid equation or the fluid PDE, and then we have the structural PDE, Now we need to connect the two, which is the boundary condition. We need to connect the two, which is the boundary condition. Okay. Now first of all, the Euler equation, which is our friend, okay, and we want to relate pressure to velocity, is let us say in the y direction in the fluid, del P by del Y okay is equal to minus rho del V by del T. Okay. So I have kind of removed T over here, so we can put T back in some way. Okay. But as I say, my time dependence is always this. Okay. So if I rewrite pressure as some spatial pressure into EI omega t, and velocity as some spatial velocity and some this EI omega t, then EI omega t can be removed. Okay. So now what I have is this del P by del Y is equal to minus I omega rho V. Okay. This V and this V are slightly different. Okay. So the upper V, this upper V is this V times e to the power I omega t. So please get used to this, otherwise I'll have to keep writing too much. Okay. So here what we are saying is this P is the coefficient of the time term and this V is the coefficient of the time term. Okay. So this is the Euler equation valid within the fluid. Okay. So what next? The next is we'll try to find out what my P, let me rewrite because it's P x comma y comma t was A, let me say e to the power of minus I k x x minus I k y y plus b e to the power of minus I k x x plus I k y y. I'll keep the time term outside. Okay. So what is del P del Y? So okay, del P del Y. What is del P del Y? Okay, so that is equal to minus I k y A e to the power minus I k x x minus I k y y plus I k y b e to the power of minus I k x x plus I k y y and the time term. Okay. Now this, suppose we evaluate this at y equal to 0. Why do we do that? We do that because in the waveguide the bottom plate velocity and the acoustic fluid particle velocity that is contiguous with the vibrating plate must be same. Okay. So, this is the y equal to 0 position. So, we evaluate the Euler equation at y equal to 0. So, at del p del y at y equal to 0 gives me minus I k y a e to the power of minus I k x x plus I k y b e to the power of minus k x x. Let us keep the time term. Okay. Now, this is equal to this term over here or this term over here. Okay. Now, what we say is that at y equal to 0, the panel displacement or plate displacement and velocity are equal to acoustic particle displacement and velocity. Okay. So, this term here, which is acoustic particle velocity, when we write it as acoustic particle velocity at y equal to 0 is equal to the plate velocity. Let us call it Vp, plate velocity, and the plate velocity is equal to I omega times W of x. Okay. So, I have this term equal to minus I omega rho into I omega W of x. I can keep e to the power I omega t because it is there. In future I will cancel it from both sides. Okay. So, this is what I have. So, if I rewrite this, what I have is omega square rho W of x is equal to minus I k y a plus I k y b e to the power of minus I k x x, where the time term I have removed. Okay. So, we are at the end of the time frame. So, I will stop over here and I will continue with this portion in the next class. Thank you.